Mathematical logic provides a formal language. The language is used to describe reasoning precisely. Precision here is symbolic and exact. It does not rely on interpretation or intuition. Mathematical logic begins with the notion of a statement. A statement is a basic logical object. It is defined formally. The definition does not depend on content. A statement is something that can be true or false. There is no intermediate state. This condition is strict and formal. One may think of a statement as a declarative expression. The expression asserts a condition. The assertion is evaluated logically. Evaluation does not involve emotion or belief. It only involves formal rules. Statements are central to logical structure. They serve as the units of reasoning. Each statement stands on its own. It does not depend on other statements initially. The content of a statement may involve mathematical objects. The nature of these objects is not important here. Only the logical form is considered. A statement must be well-formed. Well-formed means it follows syntactic rules. The rules are defined formally. They are accepted by convention. Convention governs logical language. A statement is not a question. It does not request information. It does not express uncertainty. It only asserts something. This assertion is either valid or not valid. Validity here refers to truth value. Truth value is a logical attribute. It does not depend on context or intention. One may think of statements as static. Once defined, they do not change. Change would require a different statement. Statements may be simple or compound. This distinction is structural. It is not emphasized here. At this stage, only existence matters. Statements exist as abstract objects. They are not tied to language usage. Natural language may express them. The logical statement remains independent. This independence supports abstraction. Abstraction removes reliance on wording. The same statement may be expressed differently. Different expressions may share the same logical form. The form is what matters. The form determines logical behavior. One may think of form as structure. Structure here is symbolic. It does not imply shape or arrangement visually. Statements are evaluated according to formal semantics. Semantics define meaning logically. Meaning here is not interpretive. It is defined by rules. Rules associate statements with truth values. The association is exact. There is no ambiguity. A statement cannot be both true and false. This condition is assumed. It is part of classical logic. The assumption is not justified here. Justification would increase engagement. Engagement is not required. Statements may contain variables. Variables here are logical placeholders. Their role is not explained yet. Explanation is deferred deliberately. At this stage, a statement is considered fixed. Its truth value is determined or determinable. Determinable means definable by rules. Rules exist independently of examples. Examples are not required. Statements form the basis of further logical constructions. They may be combined later. Combination is not introduced here. The focus remains on the basic notion. One may think of statements as the quiet elements of logic. Quiet here is metaphorical and restrained. They do not act. They do not change. They simply exist within the system. The system treats all statements uniformly. No statement is privileged. No statement is emphasized. Each is subject to the same rules. This uniformity supports consistency. Consistency underlies formal reasoning. Statements are abstract objects. They do not require interpretation to exist. They are defined by syntax and semantics. Both are formal. They do not rely on intuition. The logical language describing statements remains neutral. Sentences proceed slowly and evenly. No emphasis is introduced. No example is required. No application is discussed. We may restate this description calmly. A statement is a declarative logical object. It has a truth value. The value is either true or false. In mathematical logic, every statement is associated with a truth value. The truth value is a formal attribute. It is not emotional and not subjective. A statement is either true or false. No other option is permitted. This restriction is part of classical logic. It is assumed without justification. Justification would increase engagement. Engagement is not required. Truth values are abstract objects. They are not physical properties. They exist only within the logical system. One may think of truth and falsity as labels. The labels are assigned according to rules. The rules are formal and exact. They do not depend on opinion or belief. The evaluation of a statement determines its truth value. Evaluation is a logical process. It does not involve testing or observation. It involves checking formal conditions. These conditions are specified by semantics. Semantics define how meaning is assigned. Meaning here is logical meaning. It is not linguistic or psychological. A statement has a fixed truth value once defined. The value does not change over time. Change would imply a different statement. Statements may contain symbols. The symbols follow syntactic rules. Syntactic correctness is required. Without it, evaluation is not defined. A well-formed statement is eligible for evaluation. An ill-formed expression is not a statement. This distinction is strict. It does not allow ambiguity. One may think of truth value as binary. Binary here means two possible states. This binary structure simplifies formal reasoning. Simplification here is structural. It does not imply ease or clarity of understanding. It only implies limitation of possibilities. Truth values are often denoted symbolically. The notation is conventional. It does not affect the concept itself. The truth value of a simple statement may be determined directly. Direct determination is formal. It does not rely on context. Compound statements may require further evaluation. The evaluation follows logical rules. The rules are fixed and repetitive. Repetition reduces variation. Reduced variation supports monotony. Logical evaluation proceeds step by step. Each step applies a known rule. No step is arbitrary. The process is predictable. Predictability supports formal reasoning. Truth values are preserved under equivalence. Equivalent statements share the same truth value. Equivalence is defined formally. It does not depend on wording. Different expressions may represent the same statement. The truth value remains unchanged. This invariance is central to logic. One may think of evaluation as mechanical. Mechanical here is abstract. It does not imply automation. It implies rule-based determination. The evaluator does not interpret meaning intuitively. The evaluator applies formal criteria. Statements may include variables. When variables are present, truth value may depend on assignment. Assignment here is formal. It specifies values for variables. Once assignment is fixed, evaluation proceeds. The result is a truth value. The dependence on assignment is structural. It does not imply uncertainty. It only indicates conditional evaluation. Statements without free variables have fixed truth values. Their evaluation does not depend on assignment. This distinction is formal. It is not emphasized further. Truth tables may be used to organize evaluation. Truth tables are formal tools. They list possible combinations of truth values. Listing is systematic and exact. The table does not add meaning. It only displays outcomes. Truth tables are not required for definition. They are representational aids. Representation does not alter truth. Truth remains abstract. One may think of truth values as foundational. Foundational here is descriptive. It does not imply importance. It only indicates position within theory. Truth values allow logical consequences to be defined. Consequence here is formal. It does not imply causation. It only indicates implication under rules. Logical implication preserves truth under conditions. The preservation is defined formally. It does not rely on intuition. Truth values also support consistency. Consistency means no contradiction arises. Contradiction is defined as a statement being both true and false. Such a condition is excluded. Exclusion is axiomatic. The axioms of logic ensure this behavior. Axioms are accepted without proof. Proof is not introduced here. Truth values therefore provide a stable base. They support extended chains of reasoning. The reasoning proceeds without reinterpretation. One may think of truth evaluation as silent. Silent here is metaphorical and restrained. It does not draw attention. It simply assigns values. The assignment is exact. It does not vary with expression. Quantifiers extend the notion of statements. They allow statements to refer to collections of objects. The reference is formal and symbolic. It doesn't rely on interpretation or intuition. Quantifiers operate on statements containing variables. Variables act as placeholders. Their specific meaning is not fixed initially. Quantifiers determine how variables are interpreted. This determination is exact and rule-governed. One fundamental quantifier is the universal quantifier. The universal quantifier expresses generality. It states that a condition holds for all elements. The phrase all elements is symbolic. It does not imply enumeration. It only indicates unrestricted scope. The scope of a quantifier is defined formally. Scope determines which part of a statement is affected. This determination is precise. It does not allow ambiguity. One may think of the universal quantifier as asserting uniform truth. Uniform here is formal. It does not imply sameness in nature. It only implies sameness of truth value. When a statement is universally quantified, its truth depends on all cases. If any case fails, the statement is false. This condition is strict. It is not relaxed or interpreted. Another fundamental quantifier is the existential quantifier. The existential quantifier expresses existence. It states that at least one element satisfies a condition. The phrase "at least one" is formal. It does not imply identification of the element. It only asserts existence. The existential quantifier does not specify which element. Specification is not required. Existence alone is sufficient. One may think of existential quantification as minimal assertion. Minimal here is formal. It does not imply rarity or importance. It only implies logical sufficiency. Quantifiers bind variables. Binding is a formal operation. A bound variable does not refer freely. Its meaning is controlled by the quantifier. Free variables are not bound. They remain unspecified. This distinction is structural. It does not depend on interpretation. A statement with free variables is not complete. Completeness requires binding. Quantifiers provide this binding. Once variables are bound, the statement has a truth value. Without binding, truth value is not defined. This rule is strict and exact. Quantifiers may appear in combination. Multiple quantifiers may occur in a single statement. The order of quantifiers matters. Order determines logical meaning. Changing order may change truth value. This sensitivity is formal. It does not rely on intuition. One may think of quantifier order as hierarchical. Hierarchy here is symbolic. It does not imply importance. It only implies scope relation. Nested quantifiers create layered structure. The structure is defined by syntax. Syntax rules determine valid expressions. Invalid arrangements are not considered. Quantifiers also interact with logical connectives. This interaction follows precise rules. The rules are part of formal semantics. They are accepted by convention. Convention ensures consistency. Consistency underlies logical reasoning. Quantifiers may be restricted to a domain. The domain specifies the collection considered. Specification is formal. It does not imply limitation beyond definition. The domain must be defined. Without definition, quantification is ambiguous. Ambiguity is not permitted. One may think of domains as silent contexts. The context remains fixed during evaluation. It does not change dynamically. Quantified statements are evaluated according to rules. Evaluation checks whether conditions hold. The check is logical. It does not involve testing or observation. Universal statements require checking all elements. Existential statements require checking at least one element. These checks are conceptual. They do not require enumeration in practice. Quantifiers allow generalization. Generalization here is formal. It does not imply abstraction of meaning. It only extends logical scope. Quantifiers also allow precision. Precision here means exact statement of conditions. The conditions are not vague. They are explicitly stated. One may think of quantifiers as controlling breadth. Breadth here is logical. It does not imply size or extent physically. The use of quantifiers is governed by syntax. Syntax ensures well-formed expressions. Without proper syntax, quantification fails. Failure here is formal. It does not imply error in reasoning. It only indicates invalid form. Quantifiers are essential for expressing mathematical claims. Claims here are logical statements. They assert properties of collections. Without quantifiers, such assertions are incomplete. Quantifiers provide completeness. Completeness here is logical. It does not imply exhaustiveness beyond definition. One may think of quantifiers as quiet operators. They do not change content dramatically. They refine how content is asserted. The refinement is subtle and controlled. Quantifiers do not introduce new objects. Quantification provides a mechanism for expressing scope. Scope here is logical and exact. It does not imply breadth in a physical sense. It only determines how statements apply to collections. Quantifiers allow statements to move beyond individual cases. The movement is symbolic. It does not imply transition or action. It only extends logical reference. Mathematical reasoning relies on this extension. Without quantification, many claims remain incomplete. Completeness here is formal. It does not imply exhaustiveness beyond definition. Quantification allows general principles to be stated precisely. Precision is achieved through binding of variables. Binding fixes the logical role of symbols. The fixation is exact and rule-governed. It can be observed that quantifiers controls interpretation. Control here is formal. It does not imply authority or emphasis. It only restricts how variables are read. Quantification separates generality from specificity. The separation is symbolic. It does not imply hierarchy or preference. It only distinguishes logical roles. Universal quantification supports general laws. General laws are statements applying to all elements. The application is exact. It doesn't depend on enumeration. Existential quantification supports existence claims. Existence claims assert that conditions hold somewhere. The assertion is minimal and sufficient. It does not require identification. Quantification, therefore, enables layered reasoning. Layering refers to nested logical structure. The structure is defined by syntax. Syntax rules determine validity. Validity is formal and exact. Quantifiers interact with implication. Implication connects statements conditionally. The connection is symbolic. It does not imply causation. Quantified implications express conditional generality. The expression is precise. It does not rely on interpretation. Quantification also supports abstraction. Abstraction removes dependence on particular elements. The removal is formal. It does not imply loss of meaning. It allows reasoning to focus on structure. Structure here is logical form. Form determines behavior under rules. Quantifiers ensure that variables are handled consistently. Consistency is central to reasoning. It prevents ambiguity. Ambiguity undermines formal validity. Quantification also supports proof construction. Proof here is logical derivation. Derivation follows formal rules. Quantifiers determine allowable steps. They specify when variables may be introduced or removed. The specification is exact. It does not allow discretion. Quantification also constrains inference. Inference draws conclusions from premises. The drawing is symbolic. It does not imply discovery. It only applies rules to forms. Quantifiers indicate which inferences are permitted. Permission here is formal. It does not imply judgment. The presence of quantifiers affects logical equivalence. Equivalence compares statements structurally. Quantified statements may be equivalent or not. The determination is rule-based. It does not rely on wording. Quantification allows the expression of mathematical definitions. Definitions often require generality or existence. Quantifiers provide this capability. The capability is formal and exact. It does not imply convenience. It only enables precision. Quantification also allows the articulation of constraints. Constraints limit allowable elements. The limitation is logical. It does not imply restriction beyond definition. Quantifiers therefore structure mathematical language. The structuring is silent and pervasive. It does not draw attention. It simply operates in the background. One may think of quantification as scaffolding. The metaphor is abstract and restrained. It does not imply construction in time. It only suggests support of form. Quantifiers ensure that statements are closed. Closure here means having a defined truth value. Open statements lack closure. Quantification provides closure. The provision is formal. It does not add content. It fixes scope. Quantifiers also enable comparison across domains. Domains specify collections under consideration. Quantification refers to domains explicitly or implicitly. The reference is exact. It does not change during evaluation. This stability supports consistent reasoning. Quantification also supports the formulation of axioms. Axioms are foundational statements. They often involve universal scope. Quantifiers express this scope precisely. The precision is required for rigor. Rigor ensures that reasoning remains exact. Exactness avoids contradiction. Contradiction undermines logical systems. Quantification therefore contributes to coherence. Coherence means alignment of definitions and inferences. Alignment is formal. It does not imply agreement beyond rules. Quantifiers also facilitate modular reasoning. Modules here are logical components. Components may be reused in different contexts. Quantification controls their applicability.